Welcome to the deep dive. Today, we're going to be diving into a book called What If? It's written by Randall Munroe, and he also does the xkcd webcomic.
Yeah, you've probably seen it around. It's those stick figure comics.
Exactly.
Yeah.
Yeah, and this book, What If, takes these kind of like absurd hypothetical questions, right?
Like, what would happen if everyone on Earth jumped at the same time?
And then he applies real science to them.
Tries to come up with a real answer.
Yeah. And the results can be hilarious. Sometimes they can be mind-blowing. So I thought we could start with one that I always think is kind of funny. It's the question about if everyone on Earth jumped at the same time, like what would happen?
Right.
I mean, I feel like we've all wondered about that at some point, right?
Yeah, I've definitely thought about it. So he starts by, calculating the combined energy of all those people jumping.
Oh, wow.
7 billion people. And it turns out that's roughly equivalent to detonating half a ton of TNT.
Oh, wow. Okay, half a ton of TNT, that's a lot.
Yeah.
So, I mean, that would cause some serious damage, right?
You'd think so. But the Earth, you have to remember, is incredibly massive.
Right.
Compared to us puny humans. So even with all that energy, the impact on the planet's rotation is like barely even noticeable.
Oh, okay. So nothing too crazy.
No apocalyptic planet tilting.
A little bit anticlimactic, honestly.
Yeah. But here's where things get interesting. So he doesn't just stop at the physics of the jump, right?
Mm-hmm.
He also explores the sound produced by such a global leap.
Oh, yeah, that's something I never really considered. So what would it sound like? Would it just be like a giant thud?
Well, imagine like this massive sound wave rippling through the atmosphere, strong enough to be picked up by seismometers around the world.
Wow.
It wouldn't be one single sound, more like a low rumble, and that kind of crescendos and fades as the energy dissipates.
That's kind of beautiful. It makes you think about how everything's connected,
Mm-hmm.
Like even a seemingly simple action can have these global consequences.
Exactly. And it makes me think of another question that explores this idea of global impact, but this time visually.
Right.
What if everyone pointed a laser pointer at the moon at the same time?
Oh, I love that one. Would we turn it into like a giant disco ball?
That's a great image. Sadly, reality is a little less dramatic. Even with millions of laser pointers focused on one spot, the moon is just so vast and it's reflective that the effect would be, barely noticeable.
Really? I would thought, I don't know, all those lasers combined would make a difference.
It's a common misconception the light would spread out over such a huge area. So you're talking about a negligible increase in brightness.
Okay. And no lunar rave then?
No lunar rave.
That's a bummer. I guess it makes sense, I mean, the moon is pretty far away.
Yeah. Speaking of distance, want to talk about baseball?
Yes.
So specifically, what would happen if a pitcher could throw a ball at 90% the speed of light?
That's one of those questions where it's just like, whoa, what would actually happen?
Yeah, well, buckle up. Because at that speed, the baseball wouldn't just be a fastball, it'd be a relativistic projectile.
Relativistic projectile? What does that even mean?
It means we have to factor in Einstein's theory of relativity. So as an object approaches the speed of light, its mass increases exponentially.
Oh, wow.
So this baseball wouldn't just be incredibly fast, it would also become incredibly heavy.
Okay. So you have this like super fast, super heavy baseball.
Mm-hmm.
It's hurtling towards home plate. What happens? Does the bat just shatter?
It's more dramatic than that. So the ball wouldn't even reach the bat. Basically, upon entering the atmosphere, it would collide with air molecules. And that collision would release a massive amount of energy. We're talking about an explosion equivalent to a nuclear bomb.
Whoa. So more like an apocalyptic strikeout than a home run. Definitely not something you'd want to catch in the stands.
Yeah.
But what I find fascinating is how Munroe takes these absurd scenarios,
right,
and uses them to explain these pretty complex scientific concepts.
Absolutely. He breaks things down in a way that makes them, easy to grasp.
Yeah.
So let's talk about another question that highlights, the destructive potential of scientific principles. What if we tried to build a periodic table out of actual elements?
Oh, that's the one with that incredible and slightly terrifying image in the book, right?
Yeah.
It's like this visual representation of chaos.
Yeah, exactly. He doesn't shy away from the pandemonium that would erupt if you assembled all the elements in one place in their pure forms.
Right. Yeah.
You'd have explosions, fires, toxic fumes. It'd be a disaster.
Okay, so a real-life periodic table, definitely a no-go.
Yeah.
But what makes this scenario so volatile?
Well, think about the periodic table as a map of elemental personalities. You've got the alkali metals, like sodium and potassium, which are so reactive they explode on contact with water.
Right.
And then you've got the halogens, like chlorine and fluorine, which are incredibly corrosive and toxic. And let's not forget the radioactive elements. They're constantly emitting dangerous radiation.
Wow. It's like a gathering of the most volatile personalities in the universe.
Precisely. And that's why he uses this scenario to illustrate the incredible diversity and complexity of, the elements that make up our universe.
Yeah.
Each element has these unique properties and behaviors.
Yeah.
And trying to force them all together, be like mixing fire and gasoline.
Yeah. So it's safe to say we're better off admiring the periodic table as a concept than trying to actually build a physical one.
Definitely. But it's this kind of thinking that makes What If so engaging. It takes us on this journey through the bizarre and the profound. It reveals these hidden wonders and potential dangers of the scientific world.
Yeah. And it shows you that science can be really fun, too.
Exactly.
It's really interesting how Munroe doesn't just look at the physical consequences of these questions.
Yeah.
But he also kind of digs into the logistical and societal implications too.
Absolutely. Like the one where he talks about draining all of Earth's oceans.
Oh, yeah.
It sounds crazy. But he goes through and meticulously examines the ripple effects. Like everything from just immediate ecological disaster to reshaping of global trade and transportation systems.
It's like imagine entire coastal cities would just become landlocked.
Right.
And there'd be these massive land bridges connecting continents.
Yeah. It's a really cool thought experiment. But in reality, the outcome would be devastating.
Right.
You'd have the collapse of marine ecosystems.
Yeah.
And weather patterns being disrupted. Countless species would vanish.
Really underscores just how interconnected our world is. You'd think removing water would be simple.
Yeah.
But it would have these crazy catastrophic consequences.
It reminds me of another question he talks about, one that explores a more localized impact, but still very intriguing. What if everyone on Earth pointed a hairdryer at the sky?
Okay, that sounds a little silly. Even for Munroe, what kind of global havoc could a bunch of hairdryers cause?
You might be surprised. So while it wouldn't be enough to alter the Earth's rotation, the combined force of all those hairdryers, it could create some interesting microclimates.
Microclimates? You mean little pockets of warm, humid air?
Exactly. You could see localized areas with increased cloud cover, slightly elevated temperatures, maybe even altered wind patterns.
So no runaway planet. But maybe a few extra degrees and a bit more humidity.
Pretty much. It's a good reminder that even small actions,
when
you multiply them on a global scale, they can have a real effect.
Makes you think. Okay, can we go back to the baseball scenario for a second?
Sure.
You mentioned that the baseball traveling at 90% the speed of light would become incredibly heavy because of the thing called relativistic mass.
Yeah.
Can you explain that a little bit more? It sounds like, something out of a sci-fi movie.
It's one of the most mind-bending ideas in physics. So, as an object approaches the speed of light, its mass doesn't stay constant. It increases exponentially.
So the faster it goes, the heavier it gets. How's that even possible?
It all comes down to Einstein's famous equation, E-mc². Energy and mass, they're intertwined.
Okay.
As the baseball gains kinetic energy from its crazy speed, that energy is converted into mass, which makes it heavier.
So the baseball is like this concentrated packet of energy and mass.
Exactly. Hurtling through space.
And then when that energy is released...
the boom.
Yeah.
Huge explosion.
Like a tiny self-contained Big Bang.
It really makes you appreciate the power of, scientific principles, even when applied to something as ordinary as a baseball.
Totally. Okay, so let's dive into another question. This one explores the concept of density. But on a much grander scale,
All right.
What if the Earth were suddenly shrunk down to the size of a pool table?
That's a good one.
I can't even picture that. Wouldn't we all just get, squished like bugs?
The short answer is yes. But the process would be a lot more dramatic. Think about it. All the matter that makes up the Earth, compressed into the size of a pool table, the density would be unimaginable.
Right. All that mass crammed into a tiny space.
Yeah.
But what would that actually feel like? Would we even notice before we were, flattened?
It would happen instantly. The gravitational force of this mini Earth would be so strong that everything on the surface, buildings, trees, people, would be instantly pulled towards the center.
So not just squished, Right.
Exactly. The pressure and heat from this gravitational collapse, it would be so extreme that matter itself would break down.
It's almost like what happens when a black hole forms.
Right.
Yeah.
Black holes are formed when massive stars collapse under their own gravity,
Right.
and the density gets so extreme that nothing, not even light, can escape.
So this pool table-sized Earth, would it basically become like a miniature black hole?
Kind of, yeah. It wouldn't have the same mass as, a stellar black hole, but the principles are similar.
Wow.
It shows how density, gravity, and the nature of matter are all connected.
It's amazing how Munroe can connect these seemingly absurd scenarios, like fundamental concepts in physics and astronomy.
He's really good at that. Speaking of which, have you ever wondered if you could build a bridge out of chocolate?
Okay, now that's a question I can get behind. As a self-proclaimed chocoholic, I'm all ears.
All right, so it's not as crazy as it sounds. Chocolate, especially dark chocolate with a high cocoa content, it does have some structural integrity.
So there is hope for my dream of a chocolate suspension bridge.
Maybe, but there are some big challenges. The biggest one being temperature. Chocolate is very sensitive to heat. Even small changes could cause your bridge to soften and collapse.
Right, chocolate melts pretty easily. But
Yeah.
let's say we could control the temperature somehow. How much chocolate would we need to build like a small footbridge?
Well, Munroe did the math.
That's
And
right.
it turns out you'd need millions of pounds of chocolate.
Millions of pounds. That's a lot of chocolate. Okay, new plan. What if we went all out and tried to build a massive chocolate replica of the Golden Gate Bridge?
That would be amazing to see. But as Munroe points out, the logistics of that would be mind-boggling, not to mention the environmental impact of producing and transporting that much chocolate.
And let's not forget about, people trying to eat the bridge.
Yeah.
It'd be a constant battle against temptation.
That bridge would probably be more tempting than it would be structurally sound.
Okay, so maybe a full-scale chocolate bridge is a bit too ambitious, but I'm still holding out hope for a chocolate-filled future.
I like your optimism. This is what If is all about. It encourages us to embrace our curiosity and never stop asking questions, no matter how outlandish they may seem.
It's crazy how Munroe can find these common threads that connect all these seemingly random questions. Like we've talked about density when we were talking about shrinking the Earth and forming black holes, but he also talks about it with something as normal as swimming. Like the question about swimming in a spent nuclear fuel pool.
Oh, yeah.
It's not exactly your average swimming pool.
Yeah.
But he uses it to explain radiation shielding
Right.
and the density of water.
He's good at taking something that sounds scary and breaking it down into these scientific principles that are easier to understand.
So could you actually swim in one of those pools and survive?
Well, theoretically, yes. The water in those pools is super purified, and it acts as a radiation shield. But Munroe makes it clear that it's still a terrible idea.
Yeah. I mean, I imagine there are a few other things to worry about besides radiation. Like, what about the heat from the fuel rods?
Yeah, the water has to be constantly circulated and cooled down
Right.
to prevent overheating, and even brief exposure to the fuel rods themselves could be fatal.
So not exactly a relaxing swim, but it is interesting to learn about the safety measures they have in place.
Absolutely, and it shows how important density is. That dense water acts as a barrier, and it absorbs the radiation from the fuel rods. It's the same idea behind lead shielding.
Simple, but effective.
Exactly, and it goes back to that idea that even absurd questions can lead to real insights.
That's what makes Munroe's work so cool.
Definitely.
So as we wrap up our deep dive into What If,
Hmm.
what are some of the key takeaways you think our listeners should remember?
Well, I hope this encourages everyone to just be more curious. Don't be afraid to ask those what-if questions, no matter how weird they might sound.
Because curiosity is what drives scientific discovery.
Exactly. And another thing to remember is that science is everywhere.
Yeah.
Munroe shows us that we can find scientific principles at play in everything, whether it's a baseball game or a swimming pool.
It's about looking at the world with a curious mind,
Right.
always asking why and how.
And lastly, I think What If reminds us that science can be fun. Munroe's approach is playful.
Yeah.
It makes learning about these complex topics entertaining.
He shows that science doesn't have to be boring.
Right.
It can be hilarious and mind-blowing all at the same time.
I like that.
So for our listeners who are now dying to read What If, where can they find it?
You can find a link to buy the book in the episode description. I highly recommend checking it out. It's a really thought-provoking read, and it'll leave you with a new sense of wonder about the universe.
And don't forget to subscribe to our channel for more deep dives. We're always exploring new ideas and uncovering hidden gems of knowledge.
And if you like this episode, please share it with your friends. Maybe it'll spark some interesting conversations and some of their own absurd hypothetical questions.
Thanks for joining us on The Deep Dive. Until next time, keep exploring, keep questioning, and keep wondering, what if?